I'd like to talk to you today about reverse engineering the human neuromotor system and the kind of role of these properties in the design and control of wearable robots. As a disclaimer, the variable stiffness ankle that I'll talk about in this presentation has been licensed for commercial use, and I am an inventor on the pending patents. I'd like to make this thing go away. Can you see this little window? Can you see an extra window from the call on the screen or no? Okay, good.
No.
Okay, great. So the human neuromotor system is capable of amazing things. And we do this through strength and coordination and training and skill. And in a video I like to highlight that kind of shows these capabilities. Here's a professional snowboarder kind of interacting with the environment on their snowboard. And you can really tell that this person is an expert at controlling their limbs, and particularly the kind of mechanical interface between their legs and the snowboard and the ground. So these training and skill really translates to advances in motor performance. So that's the ability to regulate our joint torques or our kinetics, the ability to regulate our kinematics or body pose information, and then a concept called mechanical impedance, which is kind of the stiffness properties of the body, which I'll talk about for just a second. So mechanical impedance is really the instantaneous relationship between a perturbation displacement and the applied torque. We have lots of different mathematical forms to represent this, the most common being a second-order mechanical system consisting of inertia, damping, and stiffness. In the human body, we can regulate these properties using muscle coactivation. So muscles can only pull. So to provide motion and torque in 2 dimensions, we have agonist and antagonist musculoskeletal architecture. So by flexing these 2 muscles together, we can change the stiffness without changing the net torque or the joint's position. So we actually have independent regulation of kinetics, kinematics, in this concept, mechanical impedance. And this isn't just like a theoretical or mathematical property. This property really matters to locomotion. It describes how energy would be stored and exchanged between the joints of the leg and how disturbances go from the center of mass or from the ground to the center of mass. And these are properties that are critical for efficient, stable, and agile locomotion. We often, as roboticists, go back to biology as a blueprint for design and control. And we've really seen some amazing advancements kind of in this space. An example, agility robotics by Professor Jonathan Hurst, the Cassie robot. I believe in wearable robotics, bio-inspired dynamics could lead to kind of more natural response to disturbances, a more intuitive human-machine coupling, getting away from the feeling of sort of riding the technology that you're wearing, and really ultimately exploitation of the advanced capabilities of the human neuromotor system. So in the field of wearable robotics, we get our biologically inspired instructions by looking at tasks in 2 dimensions. We look at torques and angles and how these properties vary throughout a task. Here's an example of the ankle joint during walking. This will come up later in the talk. But this kind of 2-dimensional set of information is what we would use to design a bio-inspired system. And if we think about what system dynamics or what stiffness should the system have to replicate biology, for the past probably 100 years of biomechanics, people would take the slope of this torque angle curve and has the right units, kind of Newton meters per radian or Newton meters per degree. And they would call that the stiffness. So it would be like something like this. But as it turns out, that's not true. That's sort of mathematically inappropriate. When muscles are doing work on the body, you can't just take the slope of this curve. Stiffness is a separate property. And some work I did earlier in my career kind of made this point. So really, I'd say like one of the overarching goals of my research program is to translate this 2-dimensional information of kind of torques and angles to a new type of blueprint, a 3-dimensional set of instructions, where we can vary and control not only the torques and angles, but also the joint stiffness information. And I would call this probably one of the fundamental goals of my research program is quantifying and understanding these properties, both in context of wearable robotics, but also in the context of neuromotor control. And my hope is that we can leverage this information as a new blueprint for the design and control of assistive technology. And I'm going to talk about kind of this set of information in this talk. So the first thing I'd like to describe is how might we get mechanical impedance as a blueprint. Over the last 6 years, we've been working on these methods And this is the same torque angle relationship of the ankle. And every step, you kind of go around this cycle. And to understand the stiffness or mechanical impedance properties, we really have to interact with the limb or apply perturbations. And our approach has been to apply perturbations at kind of discrete points within the gait cycle that give us kind of snapshots of how these properties vary. And if we stack these snapshots up in time or in phase, we can get an idea for how the neuromuscular system is regulating these properties. So we've been developing these methods. This is an example of our kind of experimental paradigm. Someone walks across a walkway and they experience a slight perturbation about 2 degrees. And that blue thing in that video is a force platform. So we measure the force between the foot and the ground. And then we can fit a model, a second order mechanical model between the perturbation displacement and the perturbation response torque. And we do that using system identification techniques. So what I'd like to show you now is some of the data that we've published recently. So in this plot, we're looking at stiffness as a function of percent stance phase. In the light blue, we show data from running. And in the dark blue, we show data from walking. And the data that is particularly the new data on the walking study was the last 2 points. So what's happening during terminal stance phase. And what we showed is that the stiffness is actually much higher in the ankle joint during running, and then it has a similar profile where it increases, and then it begins to decrease in terminal stance phase, which occurs a little bit earlier in running biomechanics. And if we look at damping, we see also much different responses, and this is also consistent with the literature that the stiffness and damping, or the damping during running, would be much higher because the muscle activation is greater, and damping is known to co-vary with muscle activation. One of the exciting things I'd kind of like to highlight just for a second is that we've also been thinking about extending these methods to quantifying pathological impairments. So if you have an upper motor neuron disease like stroke or cerebral palsy, that manifests itself in changes in coordination and joint mechanics, and that inhibits mobility and makes it much more difficult for people to walk. These changes that occur, they would call in the clinic, they would call it spasticity and hypertonia, but in mechanical engineering, we would call that stiffness and damping. So we can get a kind of a insight into the changes that occur following a stroke by actually measuring the mechanical impedance as people walk. These are some data from a recent study we just completed. We're again looking at stiffness as a function of stance phase, but in this case, the lines represent, the dark blue line represents the non-paretic side of a person who's had a stroke. The light blue part is their paretic side or affected side. And then the gray is older, healthy subjects that are age and speed matched. And what we see is that the stiffness of their non-paretic side is actually much greater, and the stiffness of their paretic side is consistent with age and speed matched controls. For damping, we actually see kind of no changes or no increases in data that's consistent with the age speed match controls. And this really, I think, highlights an important point about treatment of spasticity and hypertonicity in people with stroke or cerebral palsy, where they get this information, these changes to joint mechanics, while people are seated and a therapist or clinician interacts with their joints and subjectively scores it while they're at rest on a measure between 0 and 4. And those measurements would, in the history of the literature, would say that we should see an increased stiffness and an increased damping on the paretic side, but we actually don't see that. We see no increase in damping at all, and no increase in stiffness on the affected side, where we do see a large increase on the non-affected side. And I think that's likely due, the high stiffness on the non-paretic side is likely due to the greater activation, or the harder they're working on their non-paretic side to help push themselves forward during the gait cycle. So I think these data really begin to highlight that we need a new way to quantify and assess the changes that occur post-stroke so that we can appropriately treat these patients. So going back to kind of this idea of stiffness, kind of torque and angle as a set of instructions, we can take these data from the able-bodied testing I showed first and really create this kind of 3D set of instructions. And that's what's plotted in this plot. We're looking at torque, angle, and stiffness, all co-varying during the walking gait cycle. And I'm hoping to use this as this new blueprint for design and control. And then what I'd like to talk about for the next few minutes is how we have translated this into wearable robotics. What we showed is that for the first 2/3 of the gait cycle or stance phase, a passive system can actually replicate the mechanics of the ankle. So we've designed a quasi-passive ankle foot prosthesis that can actually replicate torque, angle, and stiffness at once up until the powered kind of part of the gait cycle. So I'll tell you about this variable stiffness prosthetic foot that we've developed. So this is our technology. We call it the variable stiffness prosthetic ankle foot, or the VISPA foot for short. It has a couple innovations that I want to draw your attention to. The transmission in this system is cam-based, which allows us to specify the exact torque angle mechanics that we want. We're not confined to the mechanics of carbon fiber and leaf springs that would be consistent with today's conventional prosthetic feet. So when someone rotates their ankle joint, it deflects that spring, and we store and return energy. And like I said, we can kind of shape this torque angle biomechanics in any way that we want, which is kind of a special property of this prosthesis. The next innovation I'd like to draw your attention to is that we can change the stiffness of this foot by changing the support condition of this cantilever spring. So essentially that means we can take our custom torque angle curve and basically rotate it around the origin by modifying the support condition. So we would adjust the stiffness step to step so while the foot is unloaded. And I think this is kind of among the first variable stiffness ankle prostheses that have been developed. And another innovative design has been developed by Peter Adamczyk at Wisconsin. It's worth looking into. This is just a video of somebody walking with the system. So you'll see they store energy at heel contact, then they dissipate energy and then store it again over controlled dorsiflexion. They push off with the energy that's been stored, and you can, if you look very closely, you can see a slight underdamped response from the ankle, which just comes from its efficiency. So we used our torque angle curve to create the appropriate mechanics that would be following torque, angle, and stiffness at once for the first 2/3 of stance phase. And we tested this on the subject. So you're looking at a single subject's kinematics as a function of percent stance phase for 2 different activities. And the different lines here represent different slider positions or different stiffness configurations. And what I'd like to highlight is that we were able to vary kinematics by changing ankle stiffness, and that we were able to show a much more natural agreement with the range of motion of healthy biomechanics, in part because we can make this foot much less stiff than conventional prostheses, which are quite stiff and have a very constrained range of motion. Something I'm excited about that I mentioned earlier is that we're translating this out of the lab and it's being commercialized by a company called Willowwood. And I'm very excited to see this kind of potentially impact the lives of patients, hopefully in the next few years. So what I'd like to do now is kind of shift gears a little bit and tell you a little bit about how we've used this new system, this variable stiffness foot, to address some pretty neat questions, I think, in preference-based control. So we're going to talk about user preference now and wearable robotics. So the modern rationale for design and control of wearable robotics consists of really like 2 philosophies, I'd say. The first is kind of expert tuned based on biomechanics. So the objective here, like we've talked about in the first part of this talk, the objective here is to replicate kinetics and kinematics. There's also a relatively new philosophy called human-in-the-loop optimization, where instead of using an expert to tune based on biomechanics, the controller is tuned automatically based on a physiological objective function, which is often metabolic cost. So people are trying to tune, really the system is really tuning itself to reduce the metabolic cost of the wear. And there have been some very successful studies that have come out with this approach. But in my research group, one of the things that we think about is that people's objectives likely change over time and with different activities. It's not likely that there's one objective that's going to meet the needs for every person in every activity. In fact, people probably care about a host of different things: balance, comfort, pain, stability, effort, and the exact emphasis they might place on any one of these different items might depend on the person or the task. So one of our kind of approaches we've been exploring is the idea to use user preference as a way to gauge what the person actually wants, as sort of using all of these factors at once and letting the subject really kind of tune their own system. So what I'd like to do for kind of the next 15 minutes is tell you about 4 kind of project vignettes. So these are questions that we've been answering recently. So the first question that I'd like to discuss is, what ankle foot stiffness do people actually want? We don't know that, and in part because we never had a system that could change its properties step to step. So let's start by figuring out, what do people actually care about? The next question we asked is, how does user preference differ from clinician preference? Then we looked at what underlying mechanisms may drive preference. So what might people be sensing that's kind of governing their response? And maybe can we use this information in the future to guide the design and control of these systems? And then finally, I'll switch gears a little bit and tell you some of our more recent work on preference-based control of ankle exoskeletons. The first question we wanted to answer is, what stiffness do people actually want? So we created a CAM profile for a variable stiffness foot that was linear. So I'm showing the torque angle curve here. So it's a simple torsion spring. And people have access to change the stiffness of their foot by controlling a dial. It's mounted to their waist. So as they adjust the dial, we adjust the stiffness automatically as the foot's in swing phase between their steps. We had people walk on a treadmill. We had them find their preferred stiffness using the dial and kind of explore the space. Then we stop the treadmill, randomly receive the dial, and start over again. And we did this 5 times to not only get an estimate of what stiffness people prefer, but what is the distribution of that, or the variance associated with it. And the data looks something like this. So we're looking at preferred stiffness here for each subject. There's 2 things that I'd like to draw your attention to. The first is, people are very consistent. The coefficient of variation here is 14%. So people are actually surprisingly reliable when selecting their preferred stiffness. The next thing I'd like to point out is that people have pretty different stiffnesses by varying up to a factor of 3 or 4. And all of these subjects had about the same activity level and about the same body mass. And that means when they go to the clinic, if they went to the same clinician, they'd all get fit with the same prosthesis. But yet each person has a different preference, and in fact, these preferences span by quite a large amount. So I think this has kind of important implications in the future prescription of prostheses. And the takeaway here at this point is that people are sensitive, consistent, and diverse in the selection of their stiffness preferences. The next question we answered is, how does user preference vary from clinician preference? So this is an interesting study paradigm where we had 7 prosthetists observe 7 people with amputation during walking. Not every prosthetist observed every patient. So we had a group of prosthetists observe a single patient, and we repeated that for all subjects. Subjects walked across a walkway in front of prosthetists 39 times at 13 different stiffness values. And then each prosthetist indicated, based on observation of the person's gait, whether they think the stiffness should be increased or decreased. And then similarly, the experimental subject with amputation also noted to the experimenter whether they would like the prosthesis stiffness to increase or decrease. We use these data to create psychometric functions that describe consistency and preference associated with stiffness. I'm not going to share those exact functions in psychometric curves just because they take some time to unpack, but I have them in backup slides if anybody is interested to see them. This is an example of what the study looks like. So here's the prosthetist observing the patient. And if you look in the kind of back left corner, you see my former student, Max Shepard, who just graduated and is now actually working with Aaron Young and Greg Sawicki at Georgia Tech. These are the data from this study. So on the y-axis here, we have the percent difference of the stiffness from the below knee amputee's preference. So we're looking at, 40 here would say that the prosthetist preferred a 40% stiffer prosthesis compared to the patient. Each color here denotes a different prosthetist. And there's a few things that matter about this plot, but I really want to just draw your attention to one thing, given time constraints. It's that prosthetists prefer, on average, a much stiffer prosthetic foot, about 26% stiffer. And this did vary between clinicians and subjects, or as a function of those, but that's really important, that subjects have a preference that's much less than prosthetists. The reason why prosthetists probably prefer much stiffer feet is because that's the way feet are built today. These carbon fiber conventional prosthetic feet are quite stiff, and they're likely informed by the biomechanics that they've been seeing throughout their careers, and now sort of converge to a stiffness that's much stiffer than maybe what people actually want. The last project in this kind of series I want to tell you about is maybe what's driving preference. What are people sensing that's actually informing them of their preferences, given that they're so reliable? For this experiment, we measured 3 people that walked at fractions of their preferred stiffness. So we found their preferred stiffness, we had them walk on a treadmill, and then we had them walk at stiffness values that were plus and minus 15% and plus and minus 30% away from their preference. And we did this across 3 different speeds. We measured metabolic rate and full biomechanics using instrumented treadmill and motion capture. And we looked at how do these kinematic and metabolic factors vary with stiffness. These are the data from this. I'd like to kind of walk you through these plots from left to right. On the left-hand side, what we're showing is metabolic cost as a function of ankle stiffness, which is percent deviation from preferred. So 0 represents the subject's preferred stiffness, and then we see plus and minus 15 and plus and minus 30%. So if we look at metabolic cost, what we see is really no relationship associated with stiffness. The different colors here represent different walking speed. We see a clear trend with walking speed, but we actually don't see any trend with stiffness. So people don't seem to be selecting their stiffness based on their metabolism. In the center plot, we have peak knee flexion moment on the sound side. And what we see here is a linear relationship, which also suggests that nothing is really being optimized here. So if they wanted less or greater knee flexion moment, they would move to one of the extremes, either less stiff or more stiff. So no discernible optimum shown. But then what we did see, looking at the plot on the far right, is we're looking at cross ankle angle, root mean squared error, as a function of stiffness deviation. And what we see is a second order relationship, or a parabolic relationship, that has its vertex within, has a 95% confidence interval that includes their preference. So it looks like potentially what people are actually feeling that might be guiding their preferences is their kinematic symmetry. They want stiffness values that maximize the symmetry between their prosthetic side and their sound side. And that's a really exciting result. So the takeaways for this section of the talk are that prosthesis users prefer a much less stiff foot than what is available. Prosthesis users have diverse and consistent preferences. Prosthetists prefer a much stiffer foot. This is more like what's available today. Users are far more consistent than clinicians in the selection of their preferences, and that stems from these psychophysical curves that I can talk about in the future. And people may prefer stiffness values that improves their kinematic symmetry at the ankle joint, and that could have potentially far-reaching effects for design and assessment of these technologies. Now I'd like to take this kind of one step further and talk a little bit about a pilot study we've been doing on preference-based control of exoskeletons. So exoskeletons are also very challenging to design, tune, and control, just like prostheses. And we've been looking at an approach to control bilateral ankle exoskeletons by letting subjects kind of self-tune. And we selecting the controllers based on their preference. So the goal for the study was really to determine the controller preferences for people wearing an exoskeleton. And we looked at how these preferences change across speed. This is a pilot study, so 2 subjects, they were able to self-tune their exoskeleton. And the exoskeleton that we used was something called the Defy Exo Boot from this startup company. Defy's exoskeleton uses brushless motors, the T-Motor U8. It has a weight of about 1.35 kilograms. It's a unidirectional actuator, so it only can provide a planar flexive torque. And it has a nonlinear transmission ratio that varies between 4:1 and 17:1, depending on angle. The way that we parameterize the torque that's being provided by the exoskeleton is using peak torque timing and peak torque magnitude. So this plot shows an example of the assistance that would be provided by the exoskeleton. And this really mimics the kind of push-off phase of the gait cycle where the calf muscle is contracting and the exoskeleton is going to help push them forward. We built this into a 2-dimensional touchscreen. Here you see it on a little screen. Now we have it on a large tablet. And when subjects select on the screen, it maps their selection in 2 dimensions to these different profiles, peak torque magnitude, peak torque timing, and an example of the profiles are shown on the screen. And we asked them to explore the space and find the settings that they liked. And On this plot here, you can see the x-axis is peak torque timing, y-axis is peak torque magnitude, and you can see where they started. They sort of explored the different control parameters and then found where they liked, kind of up in the upper right-hand corner. And we repeated this again 4 to 5 times and at 3 speeds. And we get data that look like this. Here's our 2 subjects. X-axis is, again, peak torque timing. Y-axis is peak torque magnitude. And we're plotting their response. We fit a multivariate Gaussian to their data. The colors here represent the different speeds. And if we look at their profiles as a function of gait cycle, we can kind of see the differences in the profiles that they preferred across the different speeds. And there's a couple things that kind of stand out. One thing that's important is that the people's timing preferences were very consistent, both across speeds and in between subjects. But their magnitude preferences were very different. So one subject, subject 1, preferred less effort from the exoskeleton, even though they could have more or less effort if they chose to. And then subject 2 preferred much more assistance. So it kind of gets back to this, there isn't kind of maybe one size fits all. So the summary for this kind of initial study in exoskeletons is that people are able to reliably tune their own exoskeletons in 2 dimensions. Users have distinct preferences for peak torque amplitude, and really no discernible trend was observed with speed, although this is just our first 2 pilot subjects. So future work will be investigating the sensitivity and underlying mechanisms that drive preference, and similar to how we've been investigating that in our prosthetic work. So I'd like to take maybe the last 3 minutes and just tell you a little bit about our open source robotic leg. Control is one of the greatest, in my opinion, one of the greatest challenges to the widespread adoption of robotic legs. In my mind, it's why you don't see robotic legs in the public. It's very difficult to control these systems reliably and safely. And if they make a mistake, it can cause a very serious injury to the wearer. Fortunately, we have many talented researchers around the world studying the control strategies to help advance these systems out of the lab. But before someone can study their control strategies, they have to build a robotic leg. So that's inefficient because now everyone is reinventing the wheel. It costs hundreds of thousands of dollars to build one of these legs, and our community is spending this over and over and over again. And it also hinders comparisons. So it makes it difficult when people publish results to separate the impact of the hardware versus the impact of the control strategy. So our goal here was to develop an open source platform to kind of unite this field on a common hardware system on which to test their control strategies. This is our open source leg. It's a modular 2-degree of freedom system, so it can be used as an ankle or knee or both. If we look under the hood, we can see the internals here. We use motors that were developed by the drone industry that have higher torque and they're more efficient. The high torque that they provide really opens some doors in terms of design. We're able to get a lower transmission ratio, about 50 to 1, which is something like 3 to 6 times lower than what's used in conventional prostheses. We use belt drive transmissions because we have such a low transmission ratio. And we chose belt drives because they're quiet, efficient, and low cost. So they don't have long lead times associated with different manufacturers of precision machine components. We also integrated different sensing modalities into the robotic leg, including a 6-axis force torque sensor that's shown here. But there's also IMUs, there's motor current voltage, there's encoders at the joints and at the motors. And it's fully self-contained, so we want to encourage people to get out of the lab and test in the real world. So each system has an onboard battery and control embedded systems. And finally, the knee contains kind of a neat technical modification called a selectable series elastic actuator, which I'm going to skip in this talk, but I'd be happy to talk to anybody if they'd like to connect about it later. If we that's what it looks like back with its clothes on. And if this is just a quick video I wanted to show kind of us testing in our lab with our open source leg. Here, this system is being controlled by a $20 Raspberry Pi. And we've developed a set of open source Python APIs that can enable people to get up and running very, very quickly. So all of the integration between the software on the microcontroller and the brushless drive, all of that has been extracted, and it's just simple function calls. I'd like to point you to the open source leg website, opensourceleg.com. We have everything on this website that you would need to manufacture this and assemble it and control it. So we have solid model files, bill of materials, quotes, sample emails, detailed assembly instructions, detailed control instructions, software, open source data, sort of everything you need to get going. And again, the idea here was that we would be developing a platform for the research community, and I'm really excited to share that we have 8 to 9 institutions that are either using this or are building it as we speak, including Professor Aaron Young from Georgia Tech. So I just want to close with this video. This video is, highlights some of the work of our collaborator, Professor Levi Hargrove, but it just kind of, I think, shows what this leg was intended for and its capabilities, and really that we're trying to kind of get this technology out of the lab and into people's lives. This is Terry. Terry lost his leg in a motorcycle accident, and he's been helping us develop this robotic leg through collaborations for the last 3 years. So thank you. With that, I just want to close and thank my students who produced this work, my sponsors, our funding agencies, and then showcase the new robotics building that's about to open up. I will be sharing a brand new lab with Professor Robert Gregg, and I am very excited to open that building, and I hope you come check it out.